Okay, so we're going to go over a brief overview of electroanalytical chemistry. And basically, what electroanalytical chemistry is the use of electrochemistry as a tool for a measurement. So, in this scenario, the electrochemistry portion of this is going to be our signal that we're measuring, and the measurement is going to tell us something about our analyte that we're interested in. And generally, we're looking at concentration measurements. So electroanalytical chemistry is based on redox reactions. So this is going to take you back to chemistry 117 or maybe chemistry 180 if you've had that. But basically you still have to understand how to break apart a redox reaction, how to balance it, and understanding oxidation, reduction, what is an oxidizing agent, what is a reducing agent. So if we look at this overall redox reaction, the reduction half reaction is our copper 2 plus 2 electrons is going to go to copper metal with a 0 oxidation state. The oxidation half reaction of this is going to be zinc metal going to the zinc 2 plus form plus 2 electrons. And what's a little bit confusing about the terminology is that the thing that gets reduced is actually our oxidizing agent. So copper, in going from a 2 plus to a 0 oxidation state, that is reduction, and it's actually the thing that causes oxidation. So this is our oxidizing agent. And the zinc, in going from a zinc 0 to a zinc 2 plus, that's actually oxidation, but it's causing reduction, so that is our reducing agent. If it's been a while since you have assigned oxidation numbers or have balanced redox reactions, you might want to take a look at this tutorial here. It's a pretty good one that takes you through some of that. The basics of all electrochemistry is based on an electrochemical cell. And here I'm showing you a graphic of a galvanic cell or a voltaic cell, also known as a battery. And basically what we have here is we have a separation of our two half reactions which promote this electrochemical cell. So over here on the left hand side, this is the anode compartment, and anode is where oxidation occurs. And here we have zinc going to zinc 2 plus 2 electrons. And what's nice about this graphic is it's showing you actually what's going on at the surface. And so electrochemistry is a surface chemistry, and so we see at the surface of the electrode, we see that the zinc metal from this electrode is actually dissolving and turning into zinc 2 plus. Now at the other side of this electrochemical cell, we have the cathode compartment, and this is where the reduction occurs. So over here we have copper 2 plus 2 electrons going to copper 0. This is a reduction step. And again, we see what's going on at the surface. So we have copper 2 plus metal actually turning copper 2 plus ion, turning into copper metal at the surface. And so after you would let this cell run for a while, you would actually could physically measure the mass increase on this electrode, where you'd see a mass decrease happening at the surface here. So there are three characteristics to this type of electrochemical cell, which is a galvanic cell, and it's based on a spontaneous redox reaction. Okay. It has to have an external flow of electrons. If we didn't have that external flow of electrons, which we see here, we wouldn't have a current, we wouldn't be able to light the light bulb or to power our cell phone or whatever we're using a battery for. So we need that external flow of electrons. Otherwise, those electrons are going to go directly from the one system to the other. So this is why we have them physically separated and connected with this wire, this external circuit. The third component is a salt bridge. And the whole purpose of that salt bridge is simply to balance the charge. So you can't have a net flow of electrons in one direction because you build up a charge that's unstable. So we have to have some way to balance those charges. So we see here we can have a negative moving over to the anode compartment, negative ions, or we could have positive ions moving over to the cathode compartment, and in fact both of those things are happening. So if we remove the salt bridge, this electrochemical cell would not be functional anymore. So all three components are necessary for this to happen. Now, if we were going to look at this in terms of shorthand notation, what we'd see here is zinc, 1 hash mark, zinc 2 plus, a double hash mark, okay? And so in the shorthand notation, what we see is the anode is listed first. This double hash mark represents our salt bridge, followed by our cathode, so if you were shown a shorthand notation, you should be able to draw out, understand what's going on at the electrochemical cell level, or vice versa. If you were given a graphic, you should be able to indicate what's going on in shorthand notation. Okay, so way back at the beginning of the semester, we talked about two different categories of analysis methods. There are classical methods, and then there are instrumental methods. And most electrochemistry is based on instrumental methods, but there are some electrochemical measurements that are based on classical methods. And if you remember our definition from earlier, basically what we mean is they're based on stoichiometry. So in the terms of electrochemistry, where rather than using the coefficient of the molecules or the chemical species that are involved in the reaction, we're going to use the coefficient of the electrons as part of our stoichiometry and thus our calculations. And so basically there are three components or three different measurements that we can use to really get at that stoichiometry, or how much is involved with the number of electrons that are flowing. And those three components is that we could look at the charge. So charge is 1.602 times 10 to the negative 19 coulombs per electron. So that represents the charge on one electron. So if you could count charge, you would know how many electrons are being transferred in this redox reaction. You could also measure current, which is basically electron flow over time. Okay, so electron flow over time is measured in units of amperes, which is basically 1 ampere is equivalent to 1 coulomb of charge per second. And the third way that we can relate the moles of electrons to our stoichiometry is to measure potential. So potential is basically refers to, in this case, the potential energy per charge, and that's measured in volt. And so that's going to be 1 volt is equal to or equivalent to 1 joule per coulomb. So these three components allow us to get at number of electrons, which would ultimately allow us to get at how many analyte atoms are being oxidized or reduced. So if we know our balanced redox reaction, if we know how many electrons are being transferred, we know how many analyte atoms we have there. So this is one way to get at doing measurements with electrochemistry. So let's go ahead and look at an example here. In the previous two slides ago, we looked at a galvanic cell, and a galvanic cell is based on a spontaneous electrochemical reaction. But you can also have an electrolytic cell, which is basically you force a non-spontaneous reaction to occur by putting energy into the system. And so these two examples are based on electrolysis, so forcing a non-spontaneous reaction to happen. So in this first example, we're looking at the electrolysis of aqueous sodium chloride to generate Cl2. And if we take a look at the half reaction that's occurring, because ultimately we have to look at moles of electrons, so we have to look at that half reaction, we see that the chloride ion from the NaCl is turning into chlorine gas. And so we have to balance this. So we need 2 chlorides to generate 1 mole of chlorine gas, and those 2 chlorides are going to be balanced out with 2 electrons. So basically this tells us our stoichiometric relationship that for every 2 moles of electrons, we generate 1 mole of Cl2 gas. So this is, again, basic stoichiometry, but we're looking at redox and we're looking at the half reactions that are involved. So if we take a look at the information that we know 4.5 amperes are flowing for 200 minutes. So an ampere, 4.5 amperes, is equivalent to 4.5 coulombs per second. So if we multiply by unit of time, then we know how the overall charge that we have. So we're doing this current for 200 minutes. Convert minutes to seconds. Okay. So now at this point we have total charge in coulombs, but we need to get to moles and ultimately to mass of Cl2. So we have to convert our coulombs to moles of electrons. And so we know that we have 1.602 times 10 to the minus 19 coulombs per 1 electron, and we know Avogadro's number, we have 6.02 times 10 to the 23rd electrons per 1 mole of electrons. Now we're into looking at the stoichiometry, so we know 2 moles of electrons for 1 mole of Cl2, so 2 moles of electrons, 1 mole Cl2, and 1 mole Cl2 is equivalent to 70.9 grams Cl2, and if I did my math right, we end up with 19.8 grams of Cl2 generated through this process. Now, I want to point out one thing here is this factor here, the charge per 1 electron and then converting to moles of electrons, this factor is really equivalent to Faraday's constant, or the inverse of Faraday's constant actually. And Faraday's constant basically says what's the charge per mole of electrons, and Faraday's constant is 9.65 times 10 to the 4th coulomb per 1 mole of electrons. So you could simplify this down to 1 step by using Faraday's constant instead. For the second equation, I'm not going to go work through the math, but I'm going to tell you that the volts is actually irrelevant. So all you need is the amperes and the time to get to your mass of sodium that's being produced. And if you work out the math here, 2.1 times 10 to the 4th grams of sodium metal is what you generate in that electrolysis example. So give you recommend that you try that, work that one out on your own. So another approach to classical methods for electrochemistry is in titrations. So in the same way that we do acid-base titrations or EDTA titrations, you can also do redox titrations. And the math is the same, okay? The only difference is what's the chemistry that's going on to make this happen. So in a redox titration, your analyte must be redox active. So what do we mean by redox active? Your analyte must be able to accept electrons or donate electrons in an electrochemical reaction. Okay? And there are 2 approaches to detection. One detection is by using an electrode, okay? where you can measure the potential. So you can look at the change in potential as you add volume of your titrant. And the other way to do this is with an indicator. And there are some indicators that are redox active indicators, in the same way that, phenolphthalein is a weak acid base indicator kind of thing. So a good example of a redox titration indicator is starch. So starch will combine with iodine to form a blue color, and the iodine can react with a reducing agent to form iodide, the ion form, and so that blue color that's made between the iodine starch complex goes away as that iodide is formed. So this is an example of an indicator for a redox titration. Now what we have on this slide here is an example titration, and we see two different titration curves, redox titration curves. So we're plotting electrode potential versus volume of titrant added, and you can see it looks like any other titration curve that we've plotted. So we are just looking at two different analytes, and so the starting point of that potential is going to be a little bit different, but at the end of the day we're reaching that same equivalence point. So where we see that sharp S curve take place, that is our equivalence point, so we could do the same math. So it looks like at 25 milliliters, that's where we're reaching our equivalence point. So by knowing the volume and the concentration, we could backtrack to how much analyte is there based on the stoichiometry of the redox titration. You can also do derivative plots in the same way with acid-base titrations. You take a first derivative and then a second derivative. Same thing could apply for redox titration. So the math is the same, it's just based on a different type of chemical reaction. So we've talked about electrochemistry in terms of classical methods. There are also many instrumental methods that can be used for electrochemistry. But just like any other instrumental method that we've done so far, whether it's spectroscopy or chromatography, what has to happen is that that detector response has to be calibrated. So we have to generate some sort of calibration curve to model how our instrument responds to our analyte. And the way we're going to generate that calibration curve is through measuring the electrochemistry of our standards. So we're going to create a series of standards with known concentrations of our analyte, just like we do for any other instrumental method. But rather than measuring absorbance, or rather than measuring peak area like we might do for chromatography, our measurements are going to be different. So in electrochemistry, the two most common measurements that we take are either potential or current, and we can relate those back to the concentration of our analyte. Okay? So once we've created our calibration curve, we then take our sample measurement, whether it's potential or current, plug that into our calibration curve for our Y value, solve for X, and so now we know the concentration of our sample based on our calibration curve, and then backtrack the math like we've done any other time. Okay, so the premise is still the same. You create a series of standards, measure the response, create a calibration curve, and then use that calibration curve to determine how much is actually in your unknown sample. Okay, so we're going to take a look at a couple specific examples of instrumental-based electrochemistry. And probably one of the most common is ion selective electrodes. And these ion selective electrodes are a form of potentiometry. And basically in potentiometry, you're going to measure the potential, the volts, as a function of your analyte concentration. Okay. This type of setup involves two electrodes, a working electrode and a reference electrode. The working electrode is the electrode where your redox occurs. Your reference electrode is sort of the baseline by which you compare your working potential. So you have a potential that's measured across these two electrodes, which is your reference electrode is essentially your baseline. Now, the way ion selective electrodes work is that it has some sort of membrane that's going to selectively interact with the analyte of interest. And so based on the concentration of your analyte in your solution, the redox or the potential of your working electrode is going to change. That working electrode is going to be a function of how much analyte is there, which is basically based on how much interacts with your polymer membrane. So it will provide you the concentration of your analyte. And all of you have actually worked with ion selective electrodes and maybe have not realized that, because pH electrode is an example of this. Now, rather than using a polymer membrane, a pH electrode uses a glass membrane, and it turns out this glass membrane is selective to the H+ ion. So our potential is going to be proportional to how much of our hydrogen ion is present, which is an indirect measure of our pH. So that's essentially how our pH probes work. Our final example of instrumental electrochemistry is using cyclic voltammetry. This is a little more complicated than a straightforward ion selective electrode like a pH meter where you just dip it in, but this is going to involve a little bit more. So in this case, it's a form of voltammetry, and in voltammetry, you measure current as the potential is changed. This cyclic voltammetry is a 3-electrode system. It has a working electrode and a reference electrode. So similar to with the ion selective electrode, the reference electrode serves as our baseline by which we measure the potential of our working electrode. Now, the counter electrode, why we need that is because it's between the counter and the working electrode where we actually measure the current. Okay, so we need sort of both halves of the redox happening so that we have this flow of electrons so that we can measure our current. So when we take a look at kind of what that output looks like, we're looking at current as a measure or as it responds to a change in potential, and our output, what we're actually measuring, is this cyclic voltammogram, which looks kind of like a duck. People call it a duck, and it's the height of this peak, which can be used to be proportional to your analyte concentration. But this particular technique is more informative than just telling us about concentration. We can get a little information about the mechanism or kinetics based on the shape of this cyclic voltammogram. So if it's a very symmetrical voltammogram, as an example, then we know that this is a reversible redox reaction, as an example. But this is just a very, very brief overview of electrochemistry. I want you to get a sense of how you can use electrochemistry in both classical methods and instrumental methods. But basically, it's applying what you've already learned in 117 or 180 in terms of the redox reactions, just applying them to actually take a measurement. So that's it. I'll see you all in the lab.